In this activity, you're going to be looking at proportionality constants from the standpoint of unit analysis. Now, unit analysis is really pretty straightforward. Take, for example, the relationship velocity is equal to the change in displacement divided by the change in time. Well, the units of velocity, of course, everybody knows are meters per second. And that all works out because, of course, the units of displacement are meters, and the units of time are seconds. And so we can see the left side and the right side both have identical units. What happens, though, when we're dealing with a proportionality constant? So, for example, in the case of Newton's law of gravitation, and of course, Newton's law of gravitation is used to predict the force of attraction between two bodies. And those can include things on the planet Earth. They can include things like solar systems. They can include things like Moon-Earth systems. And if you look at the proportionality statement, it just makes sense. The force is in proportion to the size of the first mass, and it's directly proportional to the size of the second mass, and it's inversely proportional to the distance between the two masses squared. But we have this awkward constant, universal gravitational constant. What are the units of that constant? One thing we know for sure is that force is going to be given to us in newtons. We also know that the two masses are going to be given to us in kilogram. Similarly, the radius squared is going to be units meters times meters. So what are the units of the gravitational constant so that we end up with something that results as newtons, but we have all of these units on the right-hand side of our relationship? And so to make the unit relationships work out left to right, G, the gravitational constant, has units newtons meters squared per kilogram squared. And when you do the multiplication, kilograms and meters cancel out, and you're left with newtons.